So we have seen how energy levels are formed, formation of energy levels and definition of energy levels. So based on energy level, an energy level diagram, as we have seen in the energy level diagrams are showed like this, that we have two band, which before this chapter you were not aware of it, that what is a conduction band and what is a valence band. So this is the valence band, this is the conduction band. Now based on these two structure, how we can classify metals, insulators and semiconductors. Let's see. So classification of metals, semiconductor, metals, insulators and semiconductors. Insulators and semiconductors. Semiconductors on the basis of band theory. So first thing is the metal. So as we know, metals are very good conductor of electricity. So if you see, they have huge number density of electrons. The number density is huge. For example, iron, for example, zinc, beryllium, magnesium. These are all very good conductor of electricity. So if you see, you can classify metals. So based on their covalent band and energy band diagram, we can classify metals in two ways. First thing, two types of band structure is found. Band structure is seen in metals. Number one, either the covalent band, and the valence band. Covalent band and valence band are separated by small energy gap, In that situation, you will see the small energy gap, and the bands are partially filled. Means, if you see, this is the conduction band, this is the valence band. So there are few electrons partially filled here. All these line requires 2, maybe one is filled, and there is certain amount is partially do filled. Some of them are partially filled in, I will show you like this way, then it will be easy to understand. The gap is quite very less. The gap is very less, is less than 1 eV or something like that. So what happened is that, so this is partially filled. I will show the partially filled. This is partially filled valence band. Similarly, partially filled conduction band. They are partially filled. So, partially filled conduction band and partially filled valence band. The second case what can be observed is that the valence band and the conduction band the valence band and the conduction band overlap. So what happens is that electrons can easily go from valence band to conduction band. Even room temperature is sufficient enough to send the room temperature will be sufficient enough to send an electrons from the valence band to the conduction band. Similarly, in case of the first case also, you see as the gap is very less, Eg is less than 1 eV, as the gap is very less, so an electron which is in the valence band can easily jump to the conduction band, and sometimes when an electron loses some energy can easily fall back to the valence band. So always a mutual sharing can happen easily because of the low energy gap. So metals based on this can be easily classified. Now we'll talk about the conductivity later in case of semiconductor regarding this gap structure. So in the valence band and in the second case what we have seen is that the valence band and the conduction band overlap. So as they overlap, not fully overlap, the valence band and conduction band partially overlap. They partially overlap. So as they overlap, so electrons can easily move between. So valence electrons can easily move between conduction band and valence band. Room temperature is sufficient enough. To provide energy to an electron to jump to conduction band. This is the second structure. Now it is also observed there is something called Fermi level or Fermi energy. The highest energy level in the conduction band, filled up with electron underline it. The highest energy level in conduction band filled up with electrons at 0 Kelvin is called Fermi level. And the corresponding energy is called Fermi energy. Not the valence band, conduction band. So as they're overlapping, so much of number density, as the number density is so large, so the electrons are automatically present in the conduction band even at 0 Kelvin. So that's why metals are very good conductor, called Fermi energy. Let us come to now. So this is how we can classify. Let me draw this diagram for the second one. So they partially overlap. So this is the overlapping region. This is field conduction band. This is field valence band, and this region is the overlapping conduction band and valence band. Okay, so these are also some structure. This kind of structure is seen in case of magnesium, in case of zinc, and all this. Now let's come to insulators. Let's come to the band structure. How to classify insulators based on the, as you can guess, if the energy gap is too large, if the electrons can never ever get enough energy from the surrounding, or you cannot give enough energy to electron that it can cross such an amount of huge gap, then it is definitely an insulator. So we can see that. So insulators. In insulators, the valence band is completely filled. While the conduction band is empty. And there is a large energy gap exists. Large energy gap, I'll write it here, Eg greater than 3 electron volt exists between the two bands. It is not possible for an electron to receive sufficient energy from thermal agitation. Now what do I mean by thermal agitation? Means from the temperature. From the temperature it won't be able to get sufficient energy to overcome this gap. From the thermal agitation or by any other means to cross this gap and reach the conduction band. So it is not possible for an electron to receive sufficient energy from thermal agitation, that is from room temperature, or by any other means to cross this gap and reach the conduction bands. Hence, insulators are bad conductor of electricity at low temperature as well as at high temperature. So if I draw the band structure, you see in some cases it is, for example, a diamond. For example, a diamond, the energy gap is 7 electron volt, the energy gap. So it is a very bad conductor of electricity, and it is a very good insulator. 7 electron volt for diamond. So I'll show you the band structure here, the band diagram. As you can see, the conduction band is empty the forbidden energy gap or the valence band is very large. If you know the diagram which I have shown you, the diagram was something like this. So it went like this, no? If I'm not mistaken, something like this. From here it went to this, and then here we saw something like that. So this gap I am talking about. This gap is very large in that diagram which I was saying. So this gap is very large. It is 7 electron volt for diamond, and for normal insulators it is greater than 3 electron volt. So here you can see the valence band which is filled. But the conduction band is empty. This gap is Eg greater than 3 electron volt. So electron can never cross this gap and reach to the valence band, reach to the conduction band. So this gap is empty. Now, so empty conduction band and filled valence band. Okay. Now let us come to, so we have seen what are metals, what are insulators, how we can classify them based on the band, energy band diagram. Now let us come to semiconductors. As you can understand, if the gap is not too large, not too close, if it is within a range that electron can get sufficient energy from the surrounding temperature, then they can easily jump. They can easily make this jump and go to the conduction band, where they will get loosely attached to the nucleus, and if you give an electric field, they will easily start conducting electricity. They will jump from one conduction band to the next conduction band, and from next to next, and like that way they will drift towards in one particular direction, and there you go. You have converted a semiconductor into a conductor, which will, now let us see this. So at 0 Kelvin, the conduction band is empty. Conduction band is empty, and the valence band is filled. So a semiconductor is an insulator. At 0 Kelvin. Fine. The energy gap between the valence band and conduction band in semiconductor is less than 3 electron volt. That is Eg goes between, Eg is between, I will say Eg is greater than 1 and 1 eV to less than 3 eV. Eg is greater than equal to 1 eV to less than equal to 3 eV. Not equal to, I'll say it is less than 3 eV, something like that. So an electron at room temperature, that means on 20-25 degrees centigrade, at room temperature, few valence electrons acquire sufficient energy from thermal agitation, from thermal agitation and jumps to the conduction band and jumps to the conduction band, where they get loosely attached to the atomic nucleus, an electric field can easily drift these electrons from conduction band to conduction bands in particular direction, constituting a current. So a semiconductor is a perfect insulator at room temperature at 0 Kelvin, and as temperature increases, its conductivity increases, and at room temperature it is a very good conductor. Okay, so its conductivity is varying. So sigma is varying conductivity, which is reciprocal of resistivity. So you can see resistivity is very large. So rho for semiconductor is very large at 0 Kelvin, and it decreases with the increase in temperature. So if I draw the energy band diagram, we can see it's simple only, it's not very gap is very less. This is the conduction band, field valence band, and this is empty conduction band. So I'll show the empty conduction band with a different color, blue one. This represents the empty conduction band. This gap is Eg less than 3 electron volt. This is empty conduction band, field valence band. So this is how we classify the three metals, three things. There is conductor, we can classify metals, insulators and semiconductor based on energy band diagram.